So we're going to find the area of the surface. And it's the part of the hyperbolic paraboloid, f of xy equals x squared minus y squared, that lies within the cylinder, x squared plus y squared equals 4. So anybody remember what a hyperbolic paraboloid looks like? Yeah, it's that saddle shape, or if you like Pringles potato chips, it's that Pringles shape, right? So if you draw the saddle shape with the x-axis kind of in the screen, it might look something like this. Is one I don't expect you to be able to draw very well, but it might look something like that. You should make the final just us drawing like 4 of those. And then this guy is the origin. And that's only part of it, right? It keeps spreading out, but that's the part of it that looks like a saddle. If you actually graph this on a computer, you'll kind of see the saddle, but they show you a lot more, and it doesn't really look that much like a saddle anymore. And I drew this so that the x-axis is kind of going this way. And I know that because if I look at a cross-section of a plane, a vertical plane through the x-axis, that's the upward opening parabola, the paraboloid, parabolo part of the hyperbolic paraboloid that opens up. So what we're and I know what this looks like. In the plane, it's a circle, but in space, it's a cylinder, kind of the circular cylinder, like a Pepsi can, except it goes up forever, right, and goes down forever. And so this cylinder is going to enclose part of this paraboloid, and we should be able to find the surface area of that. So I'll bet we can do that. The formula for surface area looks just like the formula we just, well, okay, no, we didn't technically. If we change f dot n to 1, then it looks like that. So it looks like this, right? That's the formula. When the integrand on a surface integral is 1, you're finding the surface area of the surface that you're integrating over. So then you have to remember what ds is. And it's really important to remember what the formula, that if there is one, that represents your differential, if it's different than what you usually write down. So this is kind of just the representative generic formula. What's the formula for ds that gives us a way to calculate this thing? Well, you're going to end up integrating over r, right, which is kind of the shadow of s. And then ds is square root of 1 plus the partial squared. In this case, we're calling it f. So instead of calling it g sub x squared, we'll call it f sub x squared. Plus f sub y squared dA. So ds is this whole part right here. That's capital S, right? Because lowercase, so ds you think of as an infinitesimally small area of a patch of surface, right? Whereas d, that's uppercase S. D lowercase s, you think of an infinitesimally small piece of arc length, yes. And if you know that stuff, it makes it seem a lot easier after a while. It takes practice. So what does this little formula whisper to you? What does it tell you to find? And pretty soon you'll start seeing these formulas in your dreams. I pulled out the old Nintendo, the original NES system the other day. What's that? No. That's, well, was that on the original? This one looks like a little rectangular box. It had the big old cartridges that you put in. Yeah. And I pulled out a game called Metroid, a classic game from the 80s. And it looked pretty bad. It had lines down the screen. So I took it apart, read online how to clean it up. I took it apart, took an eraser to basically I think they're brass or copper connectors, I took an eraser to it, cleaned it with rubbing alcohol, and it looked perfect, and I was happy. But my son can't play Metroid. He's only 5. So I pulled out Tetris, and I cleaned that one up, and it didn't work. It just got a gray screen. And I thought my son would love Tetris. And the reason I mentioned Tetris is that very game, 30 years ago almost, I played that game so much that I saw little blocks falling in my dreams. And I had to quit playing it because it was like being awake all night, even though I was asleep, all night long. And pretty soon you're going to see these formulas in your dreams, right? But that's good. That's actually a good thing so you should stop. No. But this is more important than Tetris, right? So no, you shouldn't stop. And your brain that means your brain is processing the formula, and you're going to remember it better if you see it in your dreams. You might need a little extra sleep to make up for that, but that's okay. All right, what does this formula tell you to find? The partial. So f sub x. Look at this thing. Yeah, 2x. F sub y. Yeah, negative 2y. And then we'll just say ds then. What is ds? So ds is this whole thing. Just plug it in. Square root of 1 plus 4x squared plus 4y squared. Okay. And then dA on the end, right? Makes sense? So then our area is going to equal, okay, we'll figure out what the limits of integration are in a second, but it'll look double integral symbol, and then the ds will look like this. I think I see probably polar coordinates in our future, right? And then we have to figure out what the limits of integration are. But isn't this guy, which is kind of bound, it forms the wall, or it's the wall all the way around of, so the boundary wall all the way around of what bounds the hyperboloid, the thing you're finding the surface area of. And I think I can get away without drawing this, because if I project that wall down into the xy plane, at least I can get away without drawing it in 3D. Don't I just get a circle, radius 2? Yeah. Like that, all right? And then you think of your representative spoke. So here in this step, I'll just call it R. That's R. And then over here, I'll set it up in polar. So what does the integrand become? 1 plus 4r squared, right? You factor out the 4, you get x squared plus y squared, which is r squared. And then don't forget your area element, which in polar is r dr d theta. You see how we're, even before this chapter, we had to memorize what the differential stood for, especially if you're in like polar coordinates or cylindrical or spherical. Oh yeah, it's an area element, or it could be, if it's a triple integral, it could be a volume element. And you have to remember that particular formula. And then, okay, what does r run from? 0 to 2. And then what does theta run from? 0 to 2 pi. And it's a reasonably easy U substitution. Do you want to take it from here? All right. Yeah, so we'll stop there. That's the setup, right? And it's a reasonably easy one to do yourself. And then that way maybe we'll have time to set up another one. Well, I mean, for this cylinder, the central axis is the z-axis, right? So I wanted to avoid drawing it, but if I had to draw it, I could use the technology to help me. Because what I could do is I could draw the cylinder first, and I know it looks something like this, right? And then I could put it over here. And then, so you can kind of at least get an idea of how this thing is going to form a boundary around the hyperbolic paraboloid, because the hyperbolic paraboloid goes on forever, right? It goes down, it goes out, it goes in all directions forever, and so you need that boundary there. But if you project this guy, well, not just, you're projecting S down, the saddle shape down, but you're projecting everything down, the bounds and S, and you'll get, really, it's not just the circle. If you project the saddle down, you're getting that disc shape, aren't you?